Welcome back, everybody. Sorry for the delay. So, for me, it's a pleasure to present our next speaker, Kiran Kaur Raina, with the title Quantum Computing Meets Cryptography Building the Future on Security Technology. Kiran, the public are yours for your presentation. Thank you for us to be here for QB Hub and ABN Kiski Fest 2025.
Thank you. Thank you for having me. I think we can begin. I'll just share my screen. I hope my screen is
Oh,
visible to everyone.
yeah, we can see it. Wonderful. You
Okay.
can proceed.
Okay. Great. Great. Thank you for having me. So, today we'll be talking about quantum computing meets cryptography and how we're going to be building the future of how quantum computing is going to build the future of secure technology. And this is just a brief introduction about me. So, I've been the editor in chief of STEMI, STEM News organization, and I am currently working at an early stage quantum tech product startup. Also building my own quantum tech edtech company, and also a brand ambassador with Classic, a company that I think most of you guys might be knowing. Also create content on LinkedIn, YouTube, Medium, and Instagram and X related to quantum computing, quantum technology, courses, guidance for making your career in quantum. And I've also had a background in quantum machine learning and quantum cryptography. And right now I'm an undergraduate student at Indian Institute of Technology, Madras, where I'm studying data science and AI. That's a little bit about me, and now we will begin the session. Today we'll be covering the introduction to quantum computing, why quantum computing in the first place, um, classical cryptography, quantum cryptography, PQC and QKD, quantum blockchain, emerging quantum careers, why to join quantum computing and who should join it, and we'll end it with a Q&A session at the end. Excuse me. Um, to begin with, I'll just give like a brief introduction to what quantum computing is, just so that everybody's on the same page before we dive into quantum cryptography. I'm sure you guys know that computers run on bits, and bits are binary digits, which are represented by zeros and one, on and off, true and false. Basically, all our classical computers, the regular computers that we know, we refer to them as classical computers to distinguish between quantum computers and classical computers. And all of these regular classical computers run on bits, which are binary digits, as I said. Everything from the software, everything is basically broken down into bits, and that's how the classical computer understands what's going on. Now, when we come to qubits, which is an abbreviation for quantum bits, there's a slight difference. Um, as you can see over here in this image, classical bits are zeros and ones, but qubit, I've used a sphere to represent what a qubit can be. And this sphere is not a physical sphere, it's like a probability sphere of what the states a qubit can occupy. So it can either be, it can have the two classical states just like a classical qubit, which is 0 and 1, and it can also be a superposition state, which is in between. A superposition is like being 0 and 1 at the same time, is what I think most of you guys would have heard. That's a very, very simplified explanation of what a superposition state is. Basically, it means that after measurement, like you guys might know, after measurement, even qubits break down into classical zeros and ones. So a superposition state is representing the probability that the qubit itself, um, how much percentage it'll be a zero, it'll turn out to be a zero on measurement, and what percentage it'll turn out to be a one on measurement. Over here, this middle horizontal line over here is indicating a 50-50 state, where there's a 50% chance of it being a 0 and a 50% chance of it being a 1. So there are multiple states that a qubit can take in the superposition state as well. This is just an example of one of it. So this is, I think, a very famous picture of a quantum computer that everybody might know. And this is usually how a superconducting quantum computer looks like. Which I'm sure you guys must have seen. IBM's quantum computer, Google's quantum computer, they all look like this. There are other types of quantum computers as well. This is one of the most famous images that most of us think of or refer to while talking about quantum computers. And this entire big frame over here is known as the chandelier, and the actual chip is somewhere bottom over here attached, which is a really small chip, which I'll be showing you in the next slide. Just like these chips that have come out this year. This is Google's chip. I mean, this had come at the end of 2024, December, almost touching 2025. So Google's Willow chip, Microsoft's chip, and Amazon's chip. So these are the chips that are connected over here to this entire big chandelier. This entire chandelier is used to maintain the temperature of the qubits in the chip. That is how a quantum computer works. A superconducting quantum computer works. It requires very, very, very cold temperatures to perform. Hence, using that entire chandelier, and then there's a dilution refrigerator to cool the atoms as well. So these are the different types of quantum computers. Um, I've just mentioned a few. There are many more types as well. First off, superconducting qubits, which I had showed in the first image, and then there are neutral atoms, which QERA and Pascal are working on. There are photonic quantum computers, which I think Xanadu is working on, and PsiQuantum, and trapped ion quantum computers as well, which IonQ and Quantinuum are working on. So why did we come to start using quantum computing in the first place? Apart from its advantages for computational speed and all of that, there was also, we had reached a physical limit when it came to classical computers. There are small transistors on each classical chip that every year or every few years was reducing in size, and that's how we were able to reduce the transistor size and increase the space of it. So we had one day finally reached a limit where reducing the size of the transistor any further was making it perform like a quantum particle. So that is why we have now reached a physical limit with the transistors, and we're trying to switch to quantum computers for that case. We can't go beyond a certain limit right now physically to fit any more transistors in a chip. So now we'll start with today's topic. Um, I'm sure most of you would have already known that introduction, but I just wanted to get everybody on the same page. And now we'll go into quantum cryptography foundations. So cryptography ensures that our data stays confidential, authentic, and unaltered. And there are two main types of cryptography, key cryptography, which is symmetric key cryptography and asymmetric key cryptography. And the symmetric key cryptography is where the same key encrypts and decrypts. One example is AES. And asymmetric key cryptographies use a public key and a private key pair, such as RSA and ECC. Um, all of these rely on a mathematical problem that are hard for classical computers to solve. And quantum computers, however, redefine what hard is. So these are what classical computers use as for their cryptography algorithms. Now we will move on to just a second. I hope you can see my full screen and this is not in between. Okay, I think that's fine. Okay, just a second. Okay, yeah. Yeah, now we'll move on to the mathematics behind security. So RSA is based on the fact that factorizing large numbers is extremely time consuming for classical machines. So that is an algorithm that we use to encrypt our data and protect our data from attacks, because classical machines find it very difficult to factorize large numbers. Another one is ECC, which relies on solving elliptic curve discrete logarithmic problems. And in both cases, no efficient classical algorithm exists. That is why we trust them not to get broken by classical computers. However, the catch is that if an algorithm like Shor's algorithm can do it efficiently, that trust disappears instantly. So Shor's algorithm, I'll be talking about in the further slides, how Shor's algorithm has impacted classical computers and classical cryptography and encryption. This is the mathematics behind it. And yes, in this slide now we'll be talking about Shor's algorithm. And in 1994, Peter Shor developed Shor's algorithm, which is a factorizing algorithm that that can factor large integers and compute discrete logarithms exponentially faster than a classical algorithm. So that means that RSA, ECC, DH, the backbone of the internet encryption, would collapse, and once scalable quantum computers arrive, then there's a huge threat to them. So the other algorithm that also, um, along with Shor's algorithm, is Grover's algorithm, and that offers a different kind of attack. It halves the security strength of symmetric systems like AES, like I mentioned in the previous slide. Um, um, I can, I think I've explained it better in the next slide, which is it means that if you have a 128-bit key, these keys are long so that classical computers find it difficult to decrypt them. So if you have a 128-bit key, normally which is very secure, um, it would take 64 bits using Grover's algorithm to crack it. So it mainly affects symmetric key cryptographies like AES, and has functions used for digital signatures. So to stay secure, cryptographers double the key size. For example, if you have like a 256-bit, um, it can be decrypted like a 128-bit can be key can be decrypted. So that's one way we protect ourselves right now, by doubling the key size. Okay. So now we come to the Q day scenario. The Q day term describes the moment when a quantum computer can break current cryptography algorithms. Um, so this term you must have heard of earlier as well, which is harvest now and decrypt later. So there are that are uh, attackers and intelligence agencies that are storing encrypted data today from like healthcare sectors, financial sectors, from defense sectors, from communication, banking sectors, everywhere, that are storing encrypted data, which is the harvest now part of the phrase, and storing it to decrypt later using quantum computers in the future, once we have a scalable, sizable, workable quantum computer which can work with this. So that is a big threat, and that is the Q day scenario. And now coming to post quantum cryptography, um, this is a scenario that is used to defend against this threat. Researchers have developed post quantum cryptography algorithms that run on classical computers but can behave and that can protect against quantum attacks. So in 2024, NIST officially selected algorithms like Crystal Kyber for key exchange, and Crystal Dilithium for digital signatures. Um, so these have been selected by NIST, which is an organization that is used for validating quantum algorithms. So they have officially recognized that these algorithms can be used. And these use lattice based mathematics, which so far no quantum algorithm can efficiently solve. So we're banking on them for now. So lattice based cryptography is based on hard problems like LWE, which is learning with errors problems, especially finding structures in noisy multi-dimensional lattices. It's easy to create these lattices, but extremely difficult even for quantum computers to reverse engineer them. This makes algorithms like Kyber and Dilithium both secure and efficient enough for practical development. And many companies like Google, Cloudflare, TLS um, are working on this. Now coming to PQC adoption challenges. Um, the biggest challenge with PQC implementation is that lattice-based algorithms often have large key sizes and higher computational overhead, especially on IoT devices. and transitioning entire infrastructure from VPNs to banking systems require years of coordination and computable testing, and compatibility testing, and is also quite expensive as well. But this is a step forward to protect our systems from quantum attacks, and is highly essential, if I may say so, to do so for any organization, any country's national security. Um, so that is the only adoption challenge at the moment, but it's essential that we move towards PQC um, before quantum computers become a reality. Now let's go to quantum cryptography basics. So unlike PQC, which is still classical, quantum cryptography uses fundamental laws of physics, which is quantum mechanics and quantum physics, the properties like superposition and entanglement, and um, which I had talked about in the beginning of the session. Um, it uses that um, um, cryptography uses quantum physics basically, and one of its protocols are QKD, also known as quantum key distribution. And the key idea is that non-cloning theorems. The key idea behind QKD is non-cloning theorem, and which states that you cannot copy a quantum state without disturbing it. So, if there's an eavesdropper, you must have heard the classic example of Alice and Bob. So, if there's an eavesdropper, um, tries to intercept the communication, it's instantly detectable by both sides. So the QKD protocols are, one of it is BB84 protocol, which is a very famous protocol, which was introduced in 1984, and it is used to polarize photons to transmit random bits that become the encryption key. And if an attacker tries to measure them, the photon state changes, revealing the presence of the eavesdropper or the attacker. Sorry. Um, Another protocol is the E91 protocol, that takes this further using entanglement, and where two particles remain correlated even across large distances. That is one key factor, property of entanglement itself. And today, these systems often use decoy states, QKD, which adds random variation to prevent sophisticated photon number attacks. And now we'll talk about quantum secure direct communication. This is an emerging concept, and unlike QKD, which transmits keys between from one person to the other, um, here you actually transmit messages through quantum states, and this ensures security and integrity simultaneously, ideal for critical defense and satellite links, especially. And some real world applications would be for quantum cryptography would be quantum safe cryptography is being deployed in like many sectors, from banking to defense to healthcare. uh, every sector will be impacted. This is like the major sectors, and everything on the internet will be affected. But majorly, banks are going to be testing for quantum secure payments, and governments are going to use QKD based VPNs for military communication, and healthcare providers are exploring quantum safe data storage for long term patient confidentiality. So these are like three critical sectors that have already started moving towards PQC and QKD to protect themselves from future quantum attacks. And even cloud platforms like AWS and Azure are also incorporating post quantum algorithms into their encryption libraries. And so we're witnessing already a change in the entire scenario, that people are being more aware now of quantum cryptography and threats and PQC and all of those things. And now we'll talk about quantum blockchains. Um, Even blockchain systems face quantum risks, since they rely on ECDSA signatures. And quantum blockchain research focuses on integrating QKD um, um, for node authentication and post quantum algorithms for digital signatures, preventing future quantum miners from taking transactions. Again, just like the I said in earlier, harvest now, decrypt later. So that is also going to be a very um, like let me go back. It's going to be a very viable sector, quantum blockchain for sure, and it's fascinating because it fuses the decentralized nature of blockchain and quantum security together. So that is going to be like a nice field if you guys are interested in getting into that. So future directions would be to secure um, systems and um, incorporate quantum protocols like UKD and PQC to prevent systems from quantum attacks. And we'll be seeing an emergence of quantum internet itself, where quantum entanglement links nodes globally. And quantum safe IoT will protect billions of devices, and quantum homomorphic encryption could enable computation and encrypted data, quantum data. So that is the future directions that we are going towards, and a one that would be safer if we start implementing these protocols and start taking steps to um, like do prevention instead of cure, right? That is what we are trying to look for right now. So this is a great opportunity for people who want to get into this field. So there are a lot of career opportunities, um, or business opportunities, various opportunities that you can see. This is like another revolution, you can say. Just like the AI revolution and the AI bubble and everything started a few years back. I think now will be a great time to get into quantum computing in any field. Today we're talking about cryptography, but even quantum machine learning, quantum computing, quantum communication. There are so many fields, quantum simulation, quantum finance, that you can get into. And this entire market of quantum computing is going to be huge in about uh, a decade or so. So it's great to get like into the race right now, so that you'll be early, and then you can say that you are one of the first people to get into the quantum wave. So uh, you can see now, even on LinkedIn or different platforms, a lot of companies are saying that they're hiring for different roles, different quantum roles: the hardware side, software side, algorithm research side, programming side. So any side that you find interesting, you can go into. There are needs for quantum machine learning researchers, need for quantum software programmers, software engineers, quantum hardware engineers, um, quantum cryptography, definitely cybersecurity professionals, quantum researchers in algorithms, developing new algorithms. We need more algorithms as well. So that's another great sector to go into. So you can see that if you feel that you like physics and computer science and math and the importance of quantum computing, then this would definitely be a great sector to get into. And these are a few companies that are focused on quantum cryptography. Um, so there is Agnostic and Crypto Quantic and ID Quantic and InfiniQuant and ISRA Corporation and KETS Quantum Security, and so on and so forth. These are, I think I've taken 25, top 25 quantum cryptography companies, and this is taken from the Quantum Insider. So you can see them. I think you will be shared the slides as well, so you can go through them. I'll just pause a few seconds and let you see the list of companies. There are many more companies as well. This is just 25 from one site. Even big companies like IBM and Google and AWS, they're also focusing on quantum cryptography in multiple fields. These are companies that are more focused and just specified in one field. So, sorry, is my connection fine? I hope my connection is fine. I'll just continue. Um, yeah, so to summarize, quantum computing will eventually render current cryptography obsolete. So, however, there's no, like, it's not a doomsday situation because we have protocols and measures in place that we can use right now to protect ourselves from future quantum attacks. So, like PQC and QKD, like I mentioned, and many other as well, and a lot of research going on. And right now, um, it's a great field to get into to help in the try to develop more algorithms to prevent systems from quantum attacks, or in the future with quantum computing related algorithms as well. So it's a great time to get into this, and there's a big threat looming on all of us, for national security as well. Because just imagine if, just like earlier in the day when there was the nuclear warfare threat that was going on, that two neighboring countries, if they have a, if there's one country that has nuclear power and the neighboring country doesn't, there was always a power dynamic between them. And so having workable, relevant quantum computers will start creating that similar kind of scenario, where it will be like quantum warfare. So, in order to not reach that situation, I think all countries have to focus on quantum computing and not sleep on it, because any day anything can happen. And focusing on research and investing in research, and you yourself individually getting into the field, researching, learning, broadening your horizon. Even if you're not from the background, if you're already a professional, you can always learn. There are so many books, so many courses that you can learn from and get into this field. um, yeah, so that is just a summary of this entire topic. And why you should join it is, just like I said, a very critical scenario right now, and you can be one of the first people to join the field. And why not be a part of this important um, mission, right? So that is why you should join. And who should join? Again, if you are aligned with the mission, and if you're interested in exploring something that is still in its very native early stages, and if you like physics, maths, and computer science, and engineering, whichever side you want to go into, then definitely yes, I would say you should definitely join this um, mission. And yeah, so that's all for today, and you can follow me on these um, my social media handles. I hope it was not too short. I thought it would be longer than this, but I think now we can go on to the Q&A. Thank you.
Thank you, Kiran,
Thank
uh,
you.
for your excellent talk and all the information you have shared with us about quantum cryptography. We now have some questions, if you are agree.
Sure, sure.
Are the open source platforms or simulator you recommend for experimenting with quantum cryptography concepts?
Yeah, I would recommend, I think, Qiskit for that, since there's a lot of videos on Qiskit's own YouTube channel as well, and a lot of courses and a lot of material out there. One of the well-known quantum SDKs. So I would recommend Qiskit for sure.
Thank you, Karen. One question in the chat. In sectors like finance, defense, and communication, are there real world examples organis- where organizations are already implementing quantum safe solutions? And what are the main technical challenges in developing secure quantum protocols that can scale globally?
I'll first answer the first part. I just missed the second part. The first part, yes, I have already been hearing about multiple organizations investing in research for PQC, or organizations which are not even from a quantum background, like classical, like other finance. I mean, finance sector companies, or banking sector companies, also taking the help of other quantum startups and collaborating with them to protect their own database and systems, and ensuring that they start including PQC into their systems to protect from future quantum attacks. And I missed the second part, sorry.
Okay, the second part is what are the main technical challenge in developing secure quantum protocols that can scale globally?
Right now, since it's a very nascent field, there's a lot of research required in the field. So, and having right now, even though we have protocols, I mean, we have algorithms like Shor's algorithm and Grover's algorithm, we don't have a big enough quantum computer to actually that will be a threat to us. But once we do have that, then there are chances of like future of having threat, right? Once we reach a certain limit of qubits. Yeah.
Okay, and another question, what role do cross-disciplinary skills such as math, physics, and computer science play in building expertise in quantum security?
Yeah, just like I told you, all these algorithms are based on math, basically, and you need computer science to be able to code the algorithms. So, and physics in the quantum algorithms, you need the understanding of physics when you want to go into the research side, um, and when you're heavily invested in research. So, in that way, this is a very interdisciplinary field, and if you enjoy learning in such an interdisciplinary field, then that's a great place to join for sure.
Okay, uh, how can educators make quantum cybersecurity accessible and engaging for students who may find the topic abstract or intimidating?
Yeah, this is actually a very good question, and this is something that I'm trying to work on myself with my own edtech startup. I'm planning on making courses in quantum machine learning and quantum cryptography, quantum cybersecurity as well. So um, that is definitely a huge. There's a demand for it as well, and a huge need. I'd say that we need more of the intelligent youth to get into this field. Um, and it's an exciting field, and it's a very important field, especially even from all the other fields in quantum computing and its applications as well. I think quantum cybersecurity is super important, if I may say so, even above quantum machine learning, because it's the threat is so big that I'd say more people that get involved and take an interest would be great. And educators, the responsibility of educators is to, because this can be very complicated at so many, the math, you have to learn math and physics and computer science, and if you want to go to the engineering side. So it's definitely a huge responsibility on educators to simplify and make courses and make it accessible to students, and also not extremely expensive. Like some courses that I see are very expensive. So affordable courses. So that is a mission that I'm also working towards, and planning to make sure that this comes out by next year. So yeah, fingers crossed for that.
Thank you, Kiran. In and some questions of the chat. Can you briefly explain how quantum principles like superposition and entanglement enable computation that challenge classical encryption?
Yeah, the quantum superposition and entanglement are the fundamental building blocks of quantum physics, and then we use these quantum physics and quantum mechanics principles in our quantum algorithms, um, which are um, um, like giving power to Shor's algorithm and Grover's algorithm to increase the computational speed of these algorithms, which classical algorithms, which perform on bits, do not have the access to. They are working on classical mechanics and classical binary digits. Here, the entire nature itself, the physics itself is different, hence giving these different properties, hence increasing the speed of the algorithms, and hence um, um, leading to decrypting these current classical algorithms like RSA algorithm, just like I said, factorizing numbers, large numbers, in a much faster speed than classical computers, which is the threat that we're looking at. And there is only going to be more research in this field, and then more algorithms that can speed up things even further can happen in the future. So just being ready for all of that is very important.
Thank you. For students and researchers new to quantum cryptography, which foundational topics or skills should they focus on first?
Sorry, which skills?
Yes, what the fundamental topics or skills should they focus on first?
Okay. Basically like a beginner's roadmap, right? So I think you should first start with getting your this is just for any field in quantum computing. I'd suggest that you get your math strong, math and probability strong. So linear algebra, probability, a little bit of calculus as well, complex numbers, trigonometry. Get these basics strong. uh, they're going to be working with a lot of matrices, and so getting that strong as well. All the math part. I've actually made an entire roadmap on YouTube and a lot of posts on LinkedIn as well. I'll make a new video as well to break this down in detail. But you can check out over there so that you don't miss out what I'm saying right now. And if I miss out something, I don't want to miss out something. So definitely the math part. Uh, Focus on the math part. Secondly, focus on like basics of physics, quantum physics, like what superposition is, what entanglement is, what interference is. Just getting the basics right, and then you can move forward with a quantum SDK like Qiskit. I would suggest Qiskit since even I started with Qiskit. So there are a lot of courses that you can do on IBM Quantum's learning section. So those courses would definitely help a lot. And Qiskit's own website as well. I mean, sorry, Qiskit's own YouTube channel as well has a lot of courses, and they have this yearly what is it? Global summer school, which also explores a lot of applications. Like they've done one in just hardware, one in simulation, one in machine learning. So you can see that for sure. There are a lot of videos on YouTube as well. Apart from Qiskit, there are a lot of companies that make these YouTube videos, so you can check that out. There are some courses as well. I think that I've made a post on it on LinkedIn. I don't really remember right now for quantum cryptography a specific course at the moment. But I think yeah, there is one by NPTEL by IIT Madras. You can Google it on. I mean, you can search for it on YouTube. I think the entire playlist is there for free. So that is a good course. It's a beginner's course on quantum computing as well as quantum cryptography. So that would definitely help. And if you want to go into the quantum cryptography side, yeah, but that is further. That is later. First, complete your understanding of what gates are, what qubits are, how to program using Qiskit or any other SDK like Circ or Penny Lane. There are multiple. I'd suggest you start with Qiskit because there's already a lot of material. The only drawback with Qiskit is that they keep updating their version updates, so the code might change a little bit every twice a year or something. So just be updated with the latest updates. So then you might have to change your importing of libraries and all of that to tweak it to fit that update of that year. Um, yeah, so the math, basics of physics, beginning with a QKD, understanding how the gates work mathematically as well as in on Qiskit. Um, how to create a circuit, what components are there of a circuit, the different types of gates like a single qubit gate, a multiple qubit gate. Then start going into algorithms like Shor's algorithm, um, Grover's algorithm, multiple algorithms, so that you can go into that um, Fourier transform or all of that, and then you can pick a specialization. You can then explore quantum machine learning, quantum cryptography, quantum simulation, yeah, all of that. But for quantum machine learning and quantum cryptography as well, having an understanding of the classical fields are also important when you want to go further in that field. If you want to go into quantum machine learning, a good understanding of classical machine learning is also required. If you want to go into cybersecurity, into quantum cybersecurity, a good understanding of classical algorithms also are important. So yeah.
Thank you, Karen. Uh, I have another question. What skills or experience do you look for when hiring talent in quantum cryptography or related files?
again, just like all the basic skills that you would require for any quantum computing role, all of that, um, the math, understanding of the gates, um, using these quantum SDKs like Qiskit, Circ, understanding of them, being able to work with quantum algorithms, um, understanding the maths behind each algorithm as well, so that you can work on researching, because this is a very interdisciplinary field and a very uh, it's in a very early stage. So even if you're going to go and work in the software side, you'll still have to do research. Some amount of element of research will still be involved, even if you want to go into the programming side. Even if you want to go into the hardware side, there's some amount of software engineering that you have to learn, software programming that you'll have to do in that side. So this is a very interdisciplinary field in that way. Apart from just the subjects of like math, physics, and computer science, the research and the hardware and the programming aspect as well is very interdisciplinary in all roles. So if you want to be strictly focused on only one thing, I think then quantum is not for you. But you will be closely working with researchers if you're in a hardware role as well. If you're in a programming role as well, you'll still be working closely with researchers and doing research yourself as well. So being open to working with having a research aptitude is also very important. So these are the skills that they'll be looking at: classical cybersecurity skills, quantum skills, understanding of quantum SDKs, and being able to be flexible with programming as well as research.
Thank you, Karen. Okay. Mm, how do you see internships, research collaborations, or hackathons helping young talent break into the highline specialized file?
Especially,
Specialized file. Eh,
okay. Um, Basically how internships are helping students. Okay, internships definitely give you like hands-on experience, and depending on the kind of internship you're doing and which subject you're doing it in, if you're going for a research internship, that definitely is going to be heavily focused on research, give you a very good understanding of the math behind everything, and really having that deeper level of understanding of quantum computing and how it works will definitely take you forward in your career. Because as you keep going and becoming going into senior roles, you'll be working more and more and deeper with research. So research internships will definitely help you dive more into. You'll be reading a lot of research papers, collaborating with researchers, learning how to write your own research paper. uh, so that entire mentality, how to read a research paper, all of that will be um, involved in a research internship. And a regular project based, coding based internship as well will definitely have this research element, even though if it'll be maybe 20% of the internship, and 80% will be focused on the coding part and all that. Still there'll be a heavy emphasis on research. So you have to be ready for, just like I mentioned, if you're going for a heavily research oriented internship as well, there is a high chance of having some programming involved in that as well. And if you're going towards a programming side, project based side also, you have this chance of having a good amount of research in that aspect of it. So that is how internships help you give you hands-on advantage, hands-on experience for students. And there are courses as well that give you good technical understanding, theoretical and technical understanding. And you can experiment and play around with Qiskit and make your own projects. And there are also open source on GitHub, open source repositories. Like Qiskit is an open source repository that you can contribute to. You can see the first, there'll be some good for beginners issues over there that you can try to resolve. So that's how you can work with the software of Qiskit as well to contribute to it on GitHub. That's another good way of getting like hands-on experience. And then you can slowly start reading research papers and trying to implement research papers yourself. So these things you can do on your own, like build your own portfolio by making projects this way. So projects will definitely help, and internships will help, and doing courses will help, and hackathons again. You have like a problem statement that you have to solve for in a day or two, and you have like a few team members who will have their own um, expertise and own perspective as well and own skills. So you get to collaborate with a lot of international people as well. That's another great thing. if you're and right now it's a very compared to other streams, it's a very small pool of people right now. So compared to like classical AI and all of that, so you get to meet a lot of good people and work on great projects, and really trains your brain to think out of the box, and in that time limit how do you get a solution. So that's how hackathons help, and all of these things actually just help. So um, as much as you can do all of these things, that'll help you.
Thank you, Kyra. And one final question. If you could share one key message about quantum security with the students and researchers in Mexico and Latin America, what would it be?
Hmm. um, See, the importance of quantum security is so much for everyone, that and it's so critical right now, just like I mentioned in my entire workshop as well, that it is very very critical for us to invest in research, for students like undergraduate students and graduate students and PhDs, for all of them to invest in research, of the universities to invest in research, and as well governments to invest in the education side, so that students, even right now, even school students are high school students are starting to learn basics of quantum computing. So education that way for high school students as well would be very very beneficial, because they will have a good foundation by the time they reach their first year of undergrad, and then they can choose which side they want to go into. And the more people come into quantum cryptography and quantum cybersecurity, um, the more better it's going to be for us to find a solution to the problem that is looming on our head right now. So the QDA scenario, like I said. So it's very very crucial for everyone in the world, um, for our national security and our own personal security as well, in every which way, in every sector, the banking sectors, healthcare sectors. So I would urge governments to invest in research, heavily to invest in deep tech research, and universities as well to invest in deep tech research, and students to invest in their own skills and to self learn and self teach themselves. Even if it's not available in their own university, they may not have a course, but there are so many right now. There's so much of educational content on YouTube, on different websites, and I continuously keep posting about it on my social media, so you can definitely find there's so many sources right now. Earlier when I was starting out, there were hardly one or two courses back in 2022. So in just 3 years there have just been like a complete boom of different courses and different educational material. So definitely take advantage of it, and you'll be one of the first people to get into this field, so you can always say that and always have an edge over other people in that way. And this is a field that requires you to know classical skills, have research skills, programming skills, skills in math, physics. It's very very interdisciplinary, very interesting. So you can be like a jack of all trades, and then pick one application that you want to master in and be a master of that. So you can get into quantum cryptography that way and become a master of quantum cryptography. Yeah.
Thank you very much, Kiran, for your excellent presentation and all you share with us.
Thank you so much.